Today we start on important topics, which topics is a cluster point. Okay, first we discuss about cluster point and then we handle cluster point and use of cluster point and some specific properties and where this used in mathematics we discuss now. So we start from definition of cluster point. X is a cluster point or an accumulation point of a set E, some set E. That means X is a point. X is a cluster point of some set E if for each r greater than 0, Bxr intersection E contains a point other than X. Okay, that means we denote this one Bxr difference x equal to it denoted in it b dash xr. Okay, then this one intersection E not equal to phi, then we call x is a cluster point of E. This one is a simple definition, or I think we understand this definition clearly. So now we erase this portion and going to further discussion about this cluster point. That means we start some example, but we do it by question form. So we write every point of Z subset of R. Every point of Z subset of R is a limit point. Okay, is a limit point of Z. While Z has no cluster point. While Z has no cluster point. Okay, that means we know about that definition of limit point. Definition of limit point is some point X belongs to Z subset of R, then we construct Pxr for R greater than 0. Okay, intersection this Z not equal to phi. Okay, then this point X be a limit point of Z. So we're done limit point of Z. But if X belongs to Z, this subset of R, here we construct around the point Y, and then B dash Y R intersection Z not equal to phi. If we choose R less than 1, then this one happen. Okay, oh sorry, not equal to phi not happen, equal to phi happen, because here Y minus R, Y plus R, difference Y intersection Z equal to phi. If we construct Y equal to 1, then 1 minus R, 1 plus R, difference 1 intersection Z equal to phi. Okay, so we all understand this, I think. Then every point, if X is arbitrary, so we construct any point, then every point of Z is a limit point of Z, where every point of Z is not a cluster point. Okay, now cluster point of Q in R. Cluster point of Q in R, we erase this portion. Now construct Q. Okay, let X belongs to Q. That means cluster point in Q. Then we construct B dash XR intersection Q not equal to phi, because we know about that in any interval of R there are infinite number of rational variables. So any interval difference x deleted neighborhood of x intersection q not equal to 5. So what we do, we take this if this one is q, this then possible, if this one is q complement, then this one is possible. So we take this one is s belongs to r. Okay, then this one happen. So what we conclude, we conclude that q, that means the cluster points of q in r, the cluster point of q p r, that means cluster point set of q, the cluster point set of q b r. Understand? Next we discuss about that some familiar example. A equal to 1 by n, where n belongs to natural number. This one, a equal to 1 by n belongs to natural number. Okay, subset of r. Then we find 0 is the only cluster point of A. 0 is the only cluster point. That means how these elements are denoted. We first talk about this one. 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6, dot dot dot. Okay, here 1 by n, 1 by n plus 1 in this way. These elements are denoted. So what we do, we take any point. 1 by 4, we construct 1 by 4, then 1 by 4 minus epsilon, 1 by 4 plus epsilon intersects difference 1 by 4, intersection of A not equal to 5. When this one is equal to 5, we choose epsilon equal to minimum of 1 by 3 difference 1 by 4 and 1 by 4 difference 1 by 5. If we choose this one, then this one is 5. So we can't talk about that. 1 by 4 is a cluster point of A. Is not a cluster point. 1 by 4 is not a cluster point of A. So we erase this one. Now we denote which one is the cluster point of this set. Which one is the cluster point of this set? Which one? Just we take 0. 0 belongs to R. Then we construct one for epsilon greater than 0. Then we some deleted neighborhood. This one difference 0 intersection A not equal to 5. Why? Because this one is minus epsilon difference 0 intersection A not equal to 5. How we tell about it? Okay, because if any epsilon is any small number, we choose it epsilon equal to 1 by k. Okay, greater than 0. Then this one is minus 1 by k, 1 by k, and this one difference 0. Okay, intersection A equal to which points belong? Minus 1 by k and 1 by k. Here minus 1 by k, here 1 by k. Between here 0 and here which points it belong? Here obviously 1 by k plus 1. Okay, because we know about that k less than k plus 1, that means 1 by k plus 1 less than 1 by k, then this one is belong. Okay, and here obviously k greater than k minus 1, that means 1 by k minus 1 less than 1 by k, that means minus 1 by k minus 1 greater than minus 1 by k. Okay, then not this one if k plus 1 then this one is less than, if k plus 1 then this one is greater than, if minus then this one is possible. Okay, that means minus 1 by k plus 1, okay, less than minus 1 by, sorry, this one is greater than, that means minus 1 by k minus 1. Okay, that means first time is this one is right, here k minus 1 is right because this one is needed here. Okay, then this one is 1 by k minus 1, 1 by k plus 1. In this way, some many points is here. Many points is between this one. Okay, that means this is not equal to 5. So we do this problem. 0 is a limit point. 0 is limit point obviously, but 0 is a cluster point of it. Okay. Here we difference cluster point and limit point. Cluster point and limit point not same. Limit point just neighborhood intersection this set not equal to 5, and cluster point deleted neighborhood intersection this set not equal to 5. So now we're going to further progress of this portion. Every point of an open set U in R is a cluster point of U. Okay, we're going to this problem. We first write this problem, then discuss about this problem. So this problem is every point of a non-empty open set U in R, in is a cluster point, of U. Okay, then every point of a non-empty open set, that means phi not equal to U subset of R. Now take about that, let Y belongs to U. Then right, U be open. Open means BYR for R greater than 0. BYR, Y contain this subset of U. Obviously, this implies that Y minus R, Y plus R subset of U. So we easily handle about that. Y minus R, Y plus R, difference Y, okay, subset of U. So we talk about that this one subset of U. Then what we do? We do this intersection U not equal to phi. So Y be a cluster point of U. Then Y be arbitrary. So we write Y arbitrary. Then every point of U be an cluster point or accumulation point of U. Okay, so we do this problem so easily. This problem is too easy and we do it so simply. We are all understand about this problem. Now we're going to further discussion about one important questions. If a subset of a matrix space, then X belongs to X is a cluster point if and only if every open set contains X contains infinitely many points of it. We discuss this problem now. We write first this problem. Now we erase this portion. Okay. So what we write? Let A be a subset. Let A be a subset of X of a matrix space X of a matrix space X. Okay. Then we have to show that X belongs to X is a cluster point of A is a cluster point of A if and only if every open set containing A every open set containing X contains infinitely many points of A. Okay, then first we start this one. Every open set contains infinitely many points of A. Then this one is cluster point. Too easy. Okay. Every open set we construct U be open containing X. That means X belongs to U. And so then X belongs to U implies BXR intersection U not equal to phi. So B dash X are not equal to phi. So this one X be an accumulation point. Too easy. But now we discuss about that first portion. X belongs to X is a cluster point of A. Okay. Oh, here not U. Here would denote A. No. U subset of A. Okay. This one is okay. That means if we construct every open set, that means U is arbitrary, so every open set is do this. Now we construct further portion. X belongs to X is a cluster point. Cluster point. U subset of A, that means X is a accumulation point of A, that means X is a U, that means X is a accumulation point of A. So simply now discuss about that. X is a cluster point of A. This means so simple. B dash X are for r greater than 0. B dash X are intersection A not equal to phi. Okay. This implies that B dash X are intersection A not equal to phi. This implies that BXR intersection A not equal to phi. Okay. Then what we do? We do this one. BXR be an open set and also contained in this. Okay. This one be open set and contain in this and also contain X, and also this one contain X. Okay, that means, and this open set obviously if we construct contains finite element, then this open set obviously contains infinite element. Okay, infinitely many elements, many points of A. If we construct, if we here talk, this open set contains finitely many elements. That means if BXR intersection A equal to some these points, some finite points. Okay. this one finitely, if this open set contain x, this open set, if this one is finite, okay, then where is problem? Then we talk about that, this open set, then this open set, we choose r1 bx r1, okay, intersection a not equal to 5, if r1 equal to minimum of this x difference x r 1 less than equal to r less than. Okay, that means if this ball, this open ball contain finitely many elements, okay, then we choose about one r1 greater than 0, and this r1 contain this r1 here x, so this r1 contains some neighborhood, that means this r1 forms some neighborhood around x, and this neighborhood this neighborhood or this ball intersection a not equal to 5. So this implies that x belongs to x, not a cluster point of it. This is contradiction. Okay, so pxr contains infinitely many points of it. Understand this problem? This one is an important problem, but we discuss it too easily. Okay, now we discuss one important theorem, Bolzano-Weierstrass theorem. We erase this portion, then we discuss one important theorem. Okay, now we write first statement of this Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem. Let A be an infinite bounded subset of R. Let A be an infinite bounded subset of R. Then there is a cluster point. Then there is a cluster point of A in R. How we prove this one? Okay, A be an infinite bounded subset of R. Then there is a cluster point. Okay, we prove it now. This one is a standard theorem. So we start this proof, and we easily this one is we understand A infinite not finite, that means contains infinitely many elements. Bounded means all element bounded by some element or some point of R, and then we find there is a cluster point, that means one accumulation point of A in R. Okay, how we prove it? We prove it. Let first E equal to x belongs to R such that x less than equal to A for infinitely many A belongs to A. Okay, let M belongs to R be such that minus M less than equal to A less than equal to M for all A belongs to A. it is obviously it is obvious that minus m belongs to E. Okay, because minus m less than equal to A. Then we can easily show that E is bounded by M. We can easily show that. That means this one is so simple. X less than equal to A. Those type of X. That means this one is obviously less than equal to capital M. So we can easily show that E is bounded by capital M. Now, hence there exists L belongs to R. Hence there exists L belongs to R such that L equal to supremum of E. Okay. We claim that L is a cluster point of A. We claim that L is a cluster point of A. Okay. Now we show about this one. We need to show that we need to show that for any given L, for any L greater than 0, for any epsilon greater than 0, there exists a point. There exists a point A belongs to L difference epsilon, L plus epsilon, intersection difference L, okay, intersection A. Since then we erase some portion and we talk about then. Since L minus epsilon is not an upper bound for is not an upper bound is not an upper bound for E. There is an X belongs to E. There is an X belongs to E. There exists infinite since L minus epsilon is not an upper bound for E. There is X belongs to E such that L minus epsilon less than X. Okay, is yet not upper bound. Then X belongs to E such that this one happened. Next we show that since X belongs to E, then there exist infinitely many A. Then there exist infinitely many A belongs to A. Okay, such that X less than equal to A. Hence, there exist infinitely many A. Hence, there exist infinitely many A. infinitely many A belongs to A such that L minus epsilon less than A. Okay. Also for infinitely many such A we have also for infinitely many such A we have A less than L plus epsilon. Okay. Then we then for otherwise except for finitely many such elements of A, for all other A belongs to A, we have A greater than equal to L plus epsilon. Okay, that means A less than L plus epsilon for infinitely many such A. Otherwise, except for finitely many such elements of A, for otherwise except for except for finitely many such finitely many such A many such elements of A many such elements of A for all other A belongs to A for all other A belongs to A we have A greater than L plus epsilon. Okay, but then L plus epsilon belongs to E, but then L plus epsilon belongs to E. Okay, if this one happened, then L plus epsilon less than A, that means this L plus epsilon belongs to E. So this contradicts the fact. L equal to supremum of. Okay. Then this one can't be happen. So what we find? We find there exist infinitely many A belongs to A. There exist infinitely many A belongs to A such that L minus epsilon less than A less than L plus epsilon. In particular, there is at least one A belongs to this. There is at least one A belongs to A intersection of these. Okay, which is different from A. At least this one, which is different from A. Then L is a then that means we write it in upper portion. At least in upper portion we write it at least one A, at least one A, at least one A belongs to A intersection L minus epsilon L plus epsilon, which is different from L. Okay, then L be A and accumulation point of A. Okay, so we start about so simple example. So simple we start from E x less than equal to A some set for infinitely many A belongs to A. That means those elements which less than equal to A and which are also less than infinitely many A belongs to A. Then we construct this one is bounded, okay, and obviously then E is bounded. Then next we construct this have some supremum, and then this supremum contains infinitely many elements of A. That means at least one element A which is different from L, this suprema, and also belongs to this intersection of neighborhood of this supremum and intersection A. So, so we do it. There exists a cluster point of A in R. Okay. So today we stop here.